Um, Great. And thank you very much, Professor Joan Cordiner, for joining us today. Joan is part of the high res program, and she has very kindly agreed to come and talk for about GW Shift. I'll leave a few minutes at the end just to tell you a little bit about GW Shift and some of the things that are going on. But let's get into the slides and hear from Joan because that's what we've all turned up for. We're really looking to hear, find out about hydrogen safety and demystifying some of those elements. So, Joan, if you wanted to just go to your first slide and then do the share slide view.
Okay.
Yes, we can. The format looks a little bit weird, but let's hope that works.
Yeah. Okay. Yeah, it does seem to be taking a bit off the bottom of the slide. So, well, as you already said, I'm part of the High Res UK High Res Hub, led um, and initiated by Tim Mays, who I see is on the call, which is a hub across multiple universities, led out of the University of Bath, looking at really the high 2L challenges around uh, hydrogen. It's a big EPSRC funded hub. We've had lots of flexible funding as well that have gone out to different people, and it has four technical themes and four cross-cutting themes. And obviously, I'm here to talk about the safety aspects of that, and you can see here who the other leaders are of the different hub themes. So let's talk about hydrogen safety. There's lots we know, and it's been operated. We've made hydrogen for many, many decades. I worked on a hydrogen plant 40 years ago, made lots of hydrogen in the UK, not that we do anymore. Operated plants that use hydrogen. Really throughout my career. So, there's lots of things we know. We know how to do it safely. Like anything, it's all about making sure you understand what the issues are. But there are lots of new investors, some of who, of course, have no experience of hydrogen, new types of facilities, new technologies. There are new materials, and we'll talk a bit more about that, new conditions because the hydrogen's going to be used in different ways. And of course, we need to train and upskill people. And, I've heard some horror stories where new investors have had some incidents because they haven't understood hydrogen. We we have learned the hard way in process safety. Some would say we've learned through blood because many people have died or been injured over the last decades in safety incidents. And with all the new technology that's coming in, we don't want to learn that way. We want to learn by bringing in, right from the design stage, safety thinking in the design and the scale up, policy and regulations. For example, the gas regulations only allow for 0.1% hydrogen in a pipeline. Obviously, that's going to be a problem if we're having hydrogen pipelines. We need tools to help people who are going to be designing or operating hydrogen systems. And we also need to think about the changing climate, the changing uses over the next decades. It's not like we're we're not going from electricity to hydrogen or oil and gas to hydrogen or it's a transition, right? We use the word transition because there's a lot of moving parts, a lot of changes, different people coming on and off pipelines, different people in different parts of the supply chain having to be involved. So what are some of the big issues? Um, all of these new organizations that don't have the experience in working with hydrogen, and a lot of things, if you treat everything the same as other flammable species you've dealt with before, can give a false sense of security because hydrogen is not the same as natural gas. In some ways, hydrogen's a lot better than natural gas from a safety point of view, and in other ways, hydrogen's a lot worse. But they're definitely different, and there are things that can catch you out badly with hydrogen if you don't understand. But there are also lots of knowledge gaps. So at the moment, when we design a hydrogen plant, most hydrogen plants had the benefit of lots of space. So we could have huge separation distances, 15 meters, 30 meters of separation distance between anywhere hydrogen was and anything else. In the new modalities of using hydrogen, for example, using hydrogen on a steel plant, I'm in Sheffield, the steel plants are all in the city, surrounded by houses. Um, one organisation came to me because the planning authorities said that if they had to put their hydrogen storage in a certain place because of the look from the motorway of their building being an iconic building. But the problem is where they wanted them to put the hydrogen was pretty much right under the M1 motorway. That's not where you want to put hydrogen. And so there's, the planning authorities who are going to get involved in approving things. If you have hydrogen, for example, in the transport system, if you if you have a hydrogen filling station, how much hydrogen do you store, and then does it trigger coma regulation, coma 2 regulations, and coma 2 regulations and being able to manage successfully coma 2 site is a big undertaking. Um, but if we start to bring in some of these complicated risk-based uh, regulations in organizations that really don't have that background or history, having to handle things that have the difficulties that hydrogen has. So it has a really wide flammability range, much, much wider than pretty much anything else. So it's very, very difficult to maintain being out of the flammable zone. And if you think about startups and shutdowns, you pretty much always have to go through the flammable range. Also, cryogenic storage, obviously hydrogen liquefies at a very, very low temperature. And one of the really weird things is, if you ever get the chance to be anywhere near a hydrogen storage, is basically liquefy oxygen on the outside because the outside of the tank will be at such a low temperature that oxygen essentially condenses. And so you've got a layer of pure oxygen on the outside of the tank. So that's a bit different, right? How do you manage for that? And usually in flammable situations, the triangle you want to try and avoid having oxygen or an oxygen doning species next to a flammable. And here we have uh, hydrogen that basically creates its own pure oxygen um, because of the low temperatures. And if you think about a lot of how we make hydrogen and the new economy is essentially having hydrogen and oxygen together because we're making it from water. So the protection layers we need to have to make sure that we don't get oxygen and hydrogen together in the wrong place is really important. Hydrogen's also odorless. It's not, you can't see a hydrogen leak. It's very hard to detect. So it's pretty easy for a lot of species, if we have in natural gas, we have the smell, so and we can see a natural gas leak. That's not the same for hydrogen, so we have to train emergency responders. It's also an incredibly small molecule and it likes to leak. Um, so it's much, much more important on the containment and the maintenance and design of any pipework, of any flanges, um, of any maintenance that's done. Uh, so not only does it like to leak, and then it's hard to find the leak in a timely way to do something about it. And then the hydrogen embrittlement, it's known for a lot of materials, but of course we've got a lot of new materials coming in and new uses and how that works. And I'll tell you a bit of a horror story. I visited a plant in the US and I was asking, typically when I would go to a new plant to do some sort of auditing, I would ask, tell me what your three biggest risks are on the site and how do you manage them? And I particularly like to speak to the operators first. And this particular site that I many years later ended up being the technical director for, they told me that they stored a lot of chlorine, a lot of ammonia, and they stored hydrogen. And I asked them if they'd ever had any issues. And they told me they'd lost the whole bottom of the ammonia tank and the whole bottom of the hydrogen tank. And I said, well, that's quite concerning. Fortunately, they didn't have explosions, or, I mean, obviously, if you lose a lot of ammonia, it if you've ever been around ammonia, you know it'll get to your eyes very quickly. It's extremely toxic. Hydrogen isn't so much toxic, but of course the risk is having fire and an explosion. But it can cause asphyxiation as well. And the reason that they had this is they had been doing normal inspections, looking at just thickness measurements. But what they hadn't been looking at is looking for hydrogen embrittlement. And typically, you would do a different type of maintenance inspection, like a wet mag particle test, for example, looking at how the fibers within the metal, if they've been fractured, as you get with hydrogen embrittlement. And here we are, they'd had a release, they'd had an issue, but they still were not doing the right maintenance. So we need to train people on all these sort of special things that go around with hydrogen. So I spent a lot of my career in the US, and there is the Chlorine Institute, there is the Ammonia Producers Association, and now there are a growing networks of hydrogen uh, networks. So there's one in the US with the American Institute of Chemical Engineers, all about hydrogen safety, and a growing list of big groups in Europe and the UK working on hydrogen. So one of the things when you have a really flammable species is in your risk assessment. I mean, most legislation in the UK is about risk-based demonstration against the various codes and standards and regulations. And so typically you would have layers of protection that are needed. And obviously natural gas, for example, there are layers of protection needed there because of the high flammability. But in hydrogen, you need to have more layers of protection because it's much more likely to leak. If you do get a leak because of the very wide um, flammability zones, then you're much more likely to get an ignition. And the minimum ignition energy is very, very low. So you need extra layers of protection. And if you don't know these differences, you might do a risk assessment and just do it the way we would normally do for other kind of flammable species. And so this all needs to be handled. And because we don't necessarily have accurate information on some of the different flammable situations, the modeling of different leaks, the CFD modeling that's done is not necessarily backed by as much data as we need, and therefore we often use conservative design. And that's fine where you've got the space, for example, with the separation distances, but it's not where you've got new modalities such as lightweighting um, an aircraft and using hydrogen in aircraft. And of course, because the energy density of hydrogen is different, you need to be able to store in much more lightweighted containers. And of course, we don't know a lot about the materials uh, integrity of some of these new lightweighting materials and metals and composites, um, and how they're going to handle hydrogen. So we need a lot more data in order to improve our modeling of the different leaks and case studies that are needed to put the risk assessment and safety cases for some of the new modalities. Um, of course, we need to train and certify people. We we need new testing and maintenance protocols, particularly for new materials. We need to look at the regulatory frameworks for all of the new modalities and the new ways that hydrogen is going to be used in. And that's not just in the UK, but internationally, because we operate in a global world, and how we transport hydrogen, for example, globally, uh, needs some regulation that's joined up. And of course, emergency response planning and resourcing. If you've got now, obviously, we have hydrogen trailers going up and down motorways in the UK. People use hydrogen in the UK. Chemical plants use a lot of hydrogen, and so there are training available, and but the the potential volume of use and use outside of areas like chemical plants that are used to handling such a flammable material is going to expand. Um, and obviously, there's the public perception. And if we don't create the narrative there, others will. And, we also have a responsibility to the public to, if we're moving in with any new toxic or flammable species, that we work with the public to help them understand um, the real issues rather than the perceived issues. So, what are we doing with UK high res? The first thing we did was complete a comprehensive review of the state of the art in hydrogen safety. That just means what's in the literature, what's known, test and critique commercial consequence modeling tools, and develop bespoke solutions where appropriate for the new modalities, but also understand where the existing consequence modeling software, where the limits are. Because we can all use software and we can get answers, but how do we know these answers are right? And that's a big issue in hydrogen releases where there are a lot of problems. And even if you look up the codes and the guidance notes, and it'll tell you separation distances for hydrogen, we pretty much know that, in quite a lot of circumstances, those are not right. And how do we improve that? How do we give better guidance to companies as they start to work on hydrogen? So we said we would develop a hydrogen safety toolkit to basically, for people new coming into hydrogen, how can they get the kind of key information they need all in one place and guidance as to where to go to get the expertise they need in order to do an appropriate design, to be able to get their safety case done in a way that is uh, accurate enough, good enough, um, but also in a way that they can do it affordably. And that's, with everything in design, whether we're taking in safety, whether we're taking in environmental concerns, um, it's and I assume most of you will be aware of the concept of a LARP, as low as reasonably practical. What when we do our risk assessments, when we do our designs, how do we make sure we design in a way that gets the risk as low as reasonably practical, but also in a way that's affordable? We all know that a lot of industries left the UK, certainly in my 40-year career. There's a lot less chemical industry in the UK, and even last night at the iChemie Awards dinner, I met some former colleagues who were telling me that their jobs were being cut, and a company was moving some manufacturing out of the UK. So it's really important that when we consider safety, uh, and really any points in design, that we have good information in order to have accurate studies, to do accurate consequence modeling, so we can um, make sure we're designing things well, but still in an affordable manner. Um, that's the things we've been working on, and looking at also characterizing leaks, how we mitigate leaks, how we can improve design strategies, and looking at case studies that could be useful for companies as they go on to design new hydrogen modalities or hydrogen uses. And so we've started to look at case studies that others can use. And we've published, I'll show you some of the papers we've published already that are really not aimed as academic papers as such, but actually more aimed at giving examples for companies who are going to use hydrogen um, in some of the design and risk assessments that they are going to have to do. And so we've given some examples. So I think we've covered everything here already, talking about hydrogen being very flammable, odorless, and asphyxiant. It's very buoyant, so it rises. You can't see it. Typically, it's stored at very high pressure, and also stored at very low temperature. Um, so we did a bibliometric study on research trends in hydrogen, and you can see, there's been a lot, unsurprisingly, on hydrogen safety over the last few years, particularly storage, combustion, explosion, and ignition and propagation. The flame speed of hydrogen is much faster than natural gas, for example, as well. And what we found is, of course, a large number of papers in the last few years. And what's come out of that is the research gaps are really around quantitative risk assessment. And that's really important when you come to design, because if if you don't have good quality data, you end up putting extra layers of contingency in to make sure you're safe. Also, deflagration behaviours and explosion mitigation strategy modelling. Some safety regulations need updated, and I'll tell you a bit more about that. And really, there's some gaps in the CFD modelling of consequences. And then the other thing we found, and I'll share with you lessons learned from previous hydrogen incidents. So these are the areas that came out. Um, so, hydrogen in large scale applications, typically stored at high pressure, low temperature. We talked about oxygen condensation, high permeation and embrittlement, hydrogen leakage, and then because it's much lower density than air, it quickly spreads, so it get good dilution, which is good, but detection's difficult. But because of the wide flammability range, you need really, really, really good ventilation. And I'm afraid to say that quite a few places where I've seen hydrogen in steel shipping containers with completely inadequate ventilation. So that understanding how to make sure you are not going to go through the flammable range is really difficult, and the ventilation that you're going to need if you're going to put hydrogen in an enclosed space. Typically, in the chemical industry, we would always operate outside to improve the ventilation. But of course, in some of the new modalities, we can't do that, and therefore we have to make sure we've got calculations that are accurate enough to be able to assure us in our design. Um, so we've talked about hydrogen being easily detonable, high flame speeds, very low minimum ignition energy, and we need to do further research on hydrogen cloud diffusion and spontaneous combustion mechanisms. So, when you're doing a risk assessment, how do you know what the probability of ignition is? And how sure can we be of that data? And that's certainly areas that need more work. Um, and we really need better leak detection equipment and better sensors. And there's certainly a lot of development in sensors in the last few years, and certainly it's getting a lot better. But for example, if you're designing and you're going to put some hydrogen sensors out, how do you know where the right place to put the sensors are? How many sensors do you need? How do you know that these are going to activate in the way you expect and they're not going to get activated by other things? And if you get false positives, we all know that that can cause ignoring of signals. And then a normalization of ignoring alarms, etc. So it's really important that we have sensors we can trust. The other issues in transportation, other than the ones we've talked about, plastic lining, blistering, shrinkage in low temperature, hydrogen corrosion at high temperature as well. And of course, as we use new materials, we need to be able to measure that. At the moment in the UK, there is nowhere to do a lot of mechanical testing on liquid hydrogen. There is testing in gaseous hydrogen in the UK, particularly at the HSE and one or two other places. And there are a number of places, including us, looking at building both low and high temperature and high pressure liquid hydrogen um, testing for materials. And that's pretty much really needed. I'll give you an example in the US and Washington State, there is a place where you can do liquid hydrogen safety testing and materials. And some of the aerospace companies are telling us that they need to book more than 3 years ahead to get in there. So there's a huge need for more of that so we can do the designs. The other thing that probably a lot of people aren't aware of about hydrogen is the Joule-Thomson effect. And so, it just, when you compress gases, they get hot usually. And when you decompress gases, they get cold. Well, hydrogen, it likes to get hot. So it's just a wee bit different. And therefore, some of the standard ways we design um, that we, I guess, have become embedded in our assumptions when we do designs, we need to think differently when it comes to hydrogen. Um, there's also hydrogen safety in fuel cell vehicles. Some of you may have had the pleasure of being in the Toyota hydrogen car or Jaguar Land Rover's hydrogen tractors, or in the world's first hydrogen trains. Um, the Toyota car, just beautifully designed, really, really well designed, piece of elegant and impressive engineering. The systems are complex. Obviously, taking a filling station for hydrogen uh, becomes a coma 2 site. We have to maintain that. So we have in this country corgi gas fitters who are, have to pass and be trained to a standard to be able to work with natural gas. And we will have to do the same if we're going to have wide-scale deployment of hydrogen. My young nephew very excitedly told me a few months ago that he was going to London to train on maintaining hydrogen buses. And of course, being the meddlesome aunt, I had to make sure he heard lots about hydrogen safety and how not to take it for granted. Um, and I'm not sure if I'm excited or worried or a little bit of both that he's getting to learn how to maintain something that hopefully will take him through the rest of his career. But we want to make sure that the people who maintain these systems are well trained, that it's not just training, but they have competence, and that competence is continually measured to make sure we don't have issues with hydrogen safety. And of course, unfortunately, it just takes one really bad accident to stop a whole industry. Um, and you can see in the nuclear industry, for example, there are countries that just won't have nuclear. Um, and a hydrogen explosion could be quite public, and therefore we need to make sure we're going to do this right. This country has done really well at reducing safety incidents, um, and for many of you on this call, you might never have seen a process safety issue or an explosion, and long may that be. Unfortunately, I have seen people die at work. I have seen large releases of chemicals and explosions, and we need to make sure we learn from our past, but also that we do the right design and making sure we understand the differences. So hydrogen, for example, could be blended in the natural gas. At the moment, currently the plan is up to 20% hydrogen in natural gas. Hydrogen has a much higher diffusion coefficient compared to natural gas. The leakage obviously is much greater potential because of the small molecule. We have the hydrogen brittlement. And the other issue is a small gas, the issue of segregation. And if you're going to have a gas pipeline network and you're introducing different concentrations at different places, how do you manage that? If you've got 2% hydrogen and natural gas going in one place and you've got 20% going in another place, or there are complicated issues about how you manage that and segregation. And I know a lot of the gas network companies are doing a lot of work in that area. So we also talked about hydrogen use in aircraft, where we need new materials and we need testing for these new materials. So for example, composites, well, I don't know about you, have dealt with many like lined tanks. So like FluoroShield line tanks or PVDF line tanks or polypropylene line tanks. We know that pretty much all plastics have a permeation rate, and we know that hydrogen is absolutely wonderful at being able to permeate through things. So we need to understand that. How do we manage it? How do we measure it in real life and operation? What are the impact of fatigue? We get hydrogen embrittlement and metals, but what's going to happen in new materials, new composites? And just like I don't know if any of you have worked with fiberglass. Um, And if you realize that fiberglass also has problems, so certainly in my experience, I've seen fiberglass tanks fail catastrophically, and really there has if you imagine a tank where you're filling and emptying, filling and emptying, filling and emptying, and all the fibers in the tank are being pulled and shrunk, pulled and shrunk, pulled and shrunk. And so, certainly, one of the companies I worked for, they had 40,000 cycles as a maximum lifetime as a safety standard for how often they would fill and empty uh, um, a fiberglass tank. And, it's going to be even worse in hydrogen in any sort of composite type materials. And we need to understand all that, and we don't just now, and there's not enough testing. And so that then limits us if we're going to design. At the moment, we have to use known materials that we know how to manage it, how to test it properly, and that's going to really limit hydrogen use in aircraft, certainly for longer distances. Um, and from a safety point of view, there's not a lot of space in an aircraft. We can't have 15-meter exclusion zones in an aircraft, and the exclusion zone doesn't really mean anything because you're all in the one box. In an aircraft, you can't escape easily from an aircraft. So that just means the thoroughness of the testing, of course, is well regulated in the aircraft industry, but there's an awful lot of work that we need to do to understanding issues, to understanding and measuring so that we have good data to be able to improve our models. So that this is, we had a meeting a few weeks ago where we brought about 40 people from industry and regulators together to ask what people thought were the gaps in health and safety in the use of hydrogen and the high temperature process indices, to really look at what the challenges are and the directions. And my postdoc, Harman Preet, developed this. Um, and from the research that he's done, looking at the growing role in industry of hydrogen as an energy carrier for processes like steel, glass, and chemicals, and energy storage and industrial heating applications, really where hydrogen is going to be used to replace fossil fuels. And I thought I may as well just share with you what he came up with. Just as a reminder, the wide flammability range, the low ignition energy, the high diffusivity, sorry, and buoyancy, the invisible flames that we've talked about already, and the materials compatibility issues. The first gaps that he uncovered really are around cross sensitivity of leak detection sensors. So you can buy off the shelf just now hydrogen leak detection sensors, but the problem is they're very cross sensitive with other gases. So if you're going to particularly use it, for example, in an area where you already use other gases like natural gas or other chemical gases, how do you know you're not going to get the false positives? This very, very slow response times. A lot of the sensors have very limited operating temperature windows, and that's not going to work for where we need. They need frequent calibration and certainly poor performance in harsh environments. So there's a really big need for sensor development, and that's in this project we're not doing that, but we're really kind of advertising the need and the areas where that needs to be developed. Also, we need to develop guidance for sensor placement. We need to have validated consequence models, and we need to develop these because at the moment the consequence models for hydrogen are not where they need to be. And really being able to give designers advice on where sensor placement needs to be. How do they integrate it with other automated mitigation systems? Um, and, what about near hot process equipment? How do you handle that and how do you mitigate hydrogen leaks, potential around hot process equipment items? And so that was one area that we've been looking at where the gaps are. Obviously, we talked about hydrogen embrittlement. Um, you know, we we know there's limited data for high temperatures, long-term performance, a lack of validated materials for the new uses, and unknown effects of thermal uh, degradation and inadequate testing for novel materials. And then, if nothing else, there are certain materials you never want to be anywhere near, hydrogen, um, and that's important that that's known, and that we use materials that are tested and well understood how to manage. And we need to be able to develop these predictive degradation models so they can be adequately maintained. One of the other gaps we found was in human factors training. Now, you could say that all of this is appropriate for any high hazard chemical situation where people need to be drilled and trained in how to handle emergencies. They need to have guidelines for situation awareness and evaluation. If you're in an emergency and you can't see where the leak is, or you don't know there's a leak, then it's really difficult to understand how to manage it. And we need to provide much better specific hydrogen emergency management training. And we need a much better competency assessment frameworks for people who are going to be working in hydrogen. So I can make these slides available, but one of the things is inadequate flame detection equipment and specialist firefighting that needs to be understood and trained for, but also developing dispersion models that really meet the situations where it's going to be used in the new modalities. And of course, at the moment, we don't have enough good data to be able to model accurately all the different scenarios, and therefore we end up being overly cautious or maybe not understanding where we actually are and if we're where our risks actually are. Now, we also looked at case studies and lessons learned from hydrogen incidents, and basically the contributory root causes are to do with, unsurprisingly, undetected leaks due to sensors not working, inappropriate material selection, gaps in operator training, inadequate consequence modelling, and poor emergency coordination. Now, again, you could probably say this would be fair for any chemical, but of course, the consequences of a hydrogen explosion are high, and particularly when it's hard to detect the actual release. So the priority research areas around developing much more data around the new modalities to be able to validate consequence models, looking at hydrogen behavior in confined spaces. Typically everything that's been done in the past is all around keeping anything to do with hydrogen away from everything else, so you're not in confined spaces. And therefore, if you're doing consequence models, we know that confined spaces can make a big difference in the way the release moves, the way the ignition happens. Fire suppression effectiveness also needs to be understood, and we need to understand much better how to design hydrogen storage in the new modalities. and we need to develop much better human training and emergency response. Now, clearly, industry is very used to designing for high hazard um, fluids and chemicals. We're used to having to do comprehensive risk assessments and redundant safety systems and modelling, stakeholder consultation. We're used to doing all this, but of course we have to do it in the context of hydrogen and understanding where our models are good, where our models are bad, where we need to take extra contingency and safeguards, and also what issues that we need to be able to design for. Typically, in a chemical plant, you would have 5 layers of protection in a high hazard hydrogen leak potential case, one of them being normal control and 4 independent layers. You would have continuous monitoring, 100% training and competence management. That would be typical for any high hazard plant, and that's certainly the case for hydrogen. Ventilation is really important to get right in hydrogen, and mainly my advice to people is to go to process safety consultancies who really know what they're doing. If you've never worked with hydrogen before, this is not the time to learn on the job. You need to go to experts to make sure you're designing your safety systems properly and understanding your shutdown. So, for example, when you shut down, can you actually go through the flammable range? You might think you've had a leak, we have to shut down, but will that actually cause the explosion? So you have to think through your systems, your fire suppression systems, system segregation. So do you have all of your hydrogen in one part of your facility and oxygen handled in another part of the facility? If you're, for example, doing electrolysis, how do you keep hydrogen away from things that can cause problems? Obviously, there needs to be improved vessel codes and standards for hydrogen, particularly in new modalities and new materials. We need to have improved safety management systems, industry-specific guidelines. Now, the regulatory framework in the UK has worked fine for hydrogen in the chemical industry. And because our regulation in the UK is largely risk-based, you have to be able to do the risk assessment, and that's why our modelling becomes really important. HiSafe was a big international program of companies and universities a number of years ago, and this is where they came out with the areas that really need to have better data and better understanding, and we pretty much have found the same thing. And in order for us to design things effectively and properly and have models that work for people, we need to understand the physics of what hydrogen does when it leaks and how we can, if we don't understand how it leaks, or we don't understand and we can't model it, then we can't really know if we've got adequate mitigation systems. And so these are the areas that we really need to do. So this is the workshop that we had. We asked users, consultants, and regulators the current challenges, the common challenges, and the priority areas for work. We had a presentation from the Health and Safety Executive that reminded everybody of the legislation that can be important for hydrogen, that I'm sure many of you are very familiar with if you've been involved in safety cases at your work. Now, these are the papers that I mentioned we'd published before, just to give examples of risk assessments. And looking at some different end use of hydrogen. Claire Dunkerley from Otto Simon gave a talk on the codes and standards and the use of risk-based methodology for designing hydrogen systems, which was absolutely excellent. And of course, the talks from that are available. Industry really is leading the way with industry guidance that's been coming out over the last few years, all of which is absolutely excellent. And again, there is so much out there that, if you don't have experience in hydrogen, you really need to go to people who do have a lot of experience in hydrogen to make sure you're doing the calculations and the risk assessments properly. And we've put some excellent links for you here um, that Claire put together from Otto Simon to help people. The health and safety executive are doing a lot of work and doing a lot of testing up near Buxton at Harper Hill, where they have some hydrogen gas testing, and at the moment are looking at putting in some hydrogen liquid testing facilities, fairly large scale facilities. So there's a lot going on there, which will be really excellent. And they are also, this is the areas that they're going to be looking at leaks from liquid hydrogen bayonets, for example, ignition consequences of levies, hazard area ignition for hazard area classification, for example, for hydrogen. Of quite a few sites I have visited and looked at their disease assessments in hydrogen. Um, let's just say I've seen that are quite a lot that are need significant improvement. So if you're gonna work with hydrogen, and obviously you need to do a disease assessment, please make sure you go to a really experienced process safety company and don't pick the cheapest provider of a dossier, because I've seen some pretty poor quality dossiers over the last year or two. So this is just really important to get right, especially for hydrogen. They're also going to be reviewing safety issues related to subcoma, so less than 5 tons of hydrogen installations, because a lot of the current designs we're seeing really aren't understanding hydrogen enough to really have adequate risk assessments. And obviously they'll continue, as they always do, looking at operational experience from hydrogen and learnings. There are other projects like High Deploy in the Northwest that we've been talking with. There is also um, a lot of testing going on with Glass Futures on using hydrogen in glass plants, which is pretty much relevant to really all high temperature industries. So we're linking with them really to try and understand data from the testing so that we can build that into our models. Um, so we had this workshop on the 22nd of October, and hot off the shelf, we haven't sent it out to the workshop participants yet because we just finished this yesterday. The gaps, we asked about gaps in the standards, and what we were told is lack of clarity on crossover from natural gas to hydrogen, specific concerns about materials and components for long-term risk, safety standards perceived as vague, for example, in ATEX, where it says the word adequate, and certainly the HSE have recognised that with their starting to do work around ATEX or DESIR, as you would know it in the UK. Training and competency gas, should we have a gas save hydrogen type of certification, just like we have Corgi gas, for example, and obviously a dearth of validated data for our models, which we certainly would agree with. In projects and challenges, storage and transport of hydrogen, public roads, depending on the volumes, what are the risks? How do people manage that? Uncertainty around separation distances, that they may be insufficient for hydrogen, and certainly some of our model show that the standard separation distances that are quoted in many of the guidance documents for hydrogen are inadequate and needs much more work. Leak detection, we've talked about, training and purging procedures. So if you're using hydrogen and you're going to do some maintenance, eventually you're going to introduce some air. So how do you purge properly and not go and not have an issue when you go through the flammable range when you're removing hydrogen and entering air back into the system to do maintenance, and then equally when you go back to putting hydrogen back in the system, you will have had air in. So, and certainly we teach a process safety master's course here, and one of the things we teach is nitrogen blanketing and how to set up a nitrogen blanketing. And I would say probably 90% of all the students are absolutely gobsmacked when we teach them how to calculate um, the number of purge and release, or depending on what means you're doing to put together a hydrogen blanket, how can you calculate that you're going to do it safely? You can't just trickle a little bit of hydrogen in and think you've got a nitrogen blanket. And it's the same with when you're handling hydrogen. How do you make sure that you can establish a safe transition when you're changing concentration, and that's definitely something that needs much more careful explanation, and to make it much more widely available for all these companies that are going to start handling hydrogen, rather than waiting for every company to have to calculate it themselves. Can we put some guidance notes out? We've talked about gas detection, how to control combustion for processes like glass making, for example. Can they make the flame visible? How do they prevent flashbacks? How do you calculate? Um, in fact, one of the case studies we're looking is for a glass manufacturing company, looking at how do they prevent flashbacks and how do you calculate um, and design the pipework to make sure you go and get issues. Um, and then there's things like, what's a hydrogen compliant valve? Should we have standards for equipment for hydrogen, just like we have for chlorine, for example, or ammonia? There are valves that you can buy that are chlorine safe, or um, should we be setting some standards of materials that are safe for hydrogen, and really guidance notes on when and how to use flame arresters, how to maintain them, um, how to calculate adequate ventilation, and who are the people to ask for expertise, and should we have some sort of certification of a competent person for hydrogen? So if you're going to an engineering design company, or you're going to a process safety company, for example, to help you with design, should we be setting up a certification for hydrogen competence? Uh, and really all the other area that people were saying that they really found the hard way, that you need to engage with insurers much earlier, because obviously the insurers need to think about the design, but also regulators. It'll take a lot longer than expected. That the safety cases, obviously, in some cases, it'll be the first safety case of this particular type of new hydrogen modality. So that's really important. Really making sure that people understand the desire and hazard process, and of course that's normal for if you're in the chemical and oil and gas industry, but all of these new modalities, not necessarily people who've come from that background. Um, uh, and should we be assuming equipment is suitable, or should there be some sort of CE mark, for example, for hydrogen equipment and applications? So these are the feedback we got. Um, so we're taking this and working out what can we do within our project. We've done our comprehensive review of state of the art. That's just been submitted for publication. We've been looking at different consequence models, and looking at how we can apply that to the new modalities through a number of case studies. So if any of you have case studies of areas where you're concerned about designing hydrogen, we'd love to hear about your case studies, and perhaps we, as part of our project, can work on one of the case studies. And as part of that, we're putting together a hydrogen safety toolkit so that when new companies come along to work with hydrogen, that they can find a lot of the kind of core information they need in one place, particularly the things that are really important that you get right, that you, if you've never worked with hydrogen before, you wouldn't necessarily understand. And then applying this toolkit in an analysis of novel processes to give people examples, case studies that they can use towards developing safety cases. And we'd love your input. We're a big consortia. The whole point of this is to bring end users, bring regulators, bring process safety consultants on board so that we can actually develop something that's useful to, at the end of the day, if hydrogen's going to be part of our future, we want it to be a safe part of our future, and we want to make sure we can educate and help people design much more safely. And then separately to that, I'm also the vice president of the ICME, and part of what we started looking at as well is how can we provide training tools, not just the big week-long training courses that are really expensive for companies to send people on, but how can we put together a toolkit and continue building after the end of this UK high-rise project to continue that development to make process safety short courses and key lessons learned, etc., available for the hydrogen future. So hopefully that was helpful in giving you at least an idea of the things you need to think about for hydrogen, and uh, uh, also make you think about a few things perhaps you hadn't thought about that are things that we're going to have to grapple with in the future. And I'd love to hear your comments and challenges of where you think we should be working. Thank you.
Thank you so much, Joan. That was fascinating. A really good whistle stop tour through what is a very complex subject, and lots of areas for people to be thinking about. So I know we did run over slightly, but we kept most of the audience here because they were so interested in what you were saying. I don't think we have time for questions today, unfortunately, but we do have some questions. So I'll make sure that those come to you, and maybe we can get a
We can send
either
them out.
a verbal or a written kind of
Yeah.
response to those. That would be lovely. But I really do thank you for coming and joining and giving us so much of your time to understand more about the safety issues around hydrogen. All possible for us to work with, but definitely food for thought as we move through to making this a sustainable alternative fuel for the future. And so thank you very much. We don't have time to run through GW Shift, but I'm going to send you my slides. So there are more webinars coming up. There is training opportunities, and there is also a network with GW Shift. So all of that information will be with the slides and Joan's slides as well, which we shall provide you with afterwards. So thank you again, Joan, for joining us, and everyone have a great afternoon and a great weekend. Thank you.
Hi.